Yeah, yeah.
Okay, now you can tell me the truth. How much do you pay your son?
I was promised multiple video game sessions. I don't know about
VJ, which sandwich did you get? It's a good one. Good pick. I like their chicken salad. No, wait, no, that's not theirs that I like. It's a different one. Hello. Hey, how's it going, So Young?
Hey, can you grab lunches for
Yeah,
members?
yeah, absolutely. I don't know what they'll want, but I'll get one of each. VJ, all the forms are here in the yellow folder, but I guess we sign that at the end. If I pass. Ani. Oh yeah. I guess I don't know where people will be sitting. I guess Giuseppe already has his lunch, so I'm gonna put the ham.
To Brooklyn, you're not there.
Hi, Costas. Good.
How are you, Costas? I have a cold, that's why I'm not trying to say. There's a chair right there in the back.
I got. Yeah. Can you just post it on my Facebook profile? Just say like, tune in for James's dissertation at 11. It's at this link.
You missed ICC?
Okay, I'll do it. You can just send it to me. Yeah, no, you can. Yeah, you can hang out to me. It's send it to. Hang on. Send it to the panda. Hi, Ani.
Hello, Ani. What are the chairs? You should sit center.
Justin, are we live? Oh, okay. I think everything I say will be filtered. So now that my committee's here. Yes. I'll forward them to everybody. I'll forward them to everybody in the committee. Okay, actually, I'll just send it to you because I'm in the wrong account. Document, proposal, defense. Yes. Yeah, it does. Because I'm. Thank you. Okay, I just sent them over. It's a Google Drive link, though, because it's a big file.
So, I ran the Brooklyn half marathon.
No? This year?
Last week.
Wow.
I'm going to do the Philly half.
That is 22 seconds. I plan on the lab run on the sprint. I come to get back in case. That's great.
Should run together. Boring running.
Lab run. Lab run, yeah.
Lab run.
It is March 30th.
Oh, it's too cold.
Now it is actually too cold. The Philadelphia half marathon is always either cold or wet. But not as cold as New York. New York, the real marathon is brutal. And
It's not just like anything stuff. We got a house full of sick people.
how was the Brooklyn one?
It's boring. Brooklyn is a very ugly. I mean, there's nothing. It's terrible. The best thing is it was flat. But otherwise, that Philly half marathon is a beautiful course.
That's great.
But you did the run?
Last week. Getting into it.
That's good. I'm way more than the time. I had more time ago.
What's that?
I had more time ago. Yeah, if it's well, it's IM. Right?
CJ, I grabbed some lunches. Oh, Ani also, I grabbed some lunches in there. Okay. If you like any of these.
Annie, are you the chair?
Yes, I am the chair. So I was just okay. So let's go ahead and start. So this is James' PhD defense, right? This is defense. And so the way we're going to do this is we're going to have your presentation, and then we're going to go into our public section and Q&A. And then once that is done, I'm going to invite the audience to step out, and if we have audiences online, we'll ask them to disconnect, and then we'll go through the private portion of our Q&A with the committee. And then once that is done, we're going to ask you to step out of the room while we deliberate, and then we will invite you back to let you know what the topics are. Okay, so without further ado, please go ahead.
Okay. Hello, everybody. Thank you for coming out. I really appreciate it. My name is James Svacha, and I'm going to be presenting my dissertation defense on estimation and control of quadrotors using an IMU and leveraging aerodynamic effects. So the outline of my talk is going to be first, I'm going to present an introduction, followed by preliminary information and my past work, which is the work I did before my proposal on quadrotor aerodynamic modeling, control, and state estimation. Since I'm pressed for time, I will be spending most of my time on the work that I've done since my proposal, which is the inertia estimation and wind estimation for quadrotors. So let's delve into the introduction. The problem statement is basically, can we use an aerodynamic model to extract more information out of an IMU than would otherwise be possible? So traditionally, the IMU, specifically the accelerometer, is used in a kinematic model. And what we would like to do is use it in a dynamic model that expresses the dynamics as a function of the full state of the quadrotor, as well as the motor speeds of the being commanded to the quadrotor. We want to use those in the dynamic model as well. And we want to use this state estimation paradigm to estimate inertial parameters and wind velocity as well. The challenges to this are mainly that we are being forced now to consider, since we're adding the rotation dynamics into the system, we're being forced to consider the aerodynamic moments acting on the vehicle. Some of those we expected, we did not think were going to be significant, and they completely blindsided us. And another challenge is that our system with only the IMU is unobservable in hover. And therefore, we have to design some rich trajectories that simulate the system and get it far away from hover. So the impact of this work is basically on package delivery. For inertial parameter estimation, this is important because when we're doing package delivery, we're constantly picking and placing packages, and that constantly changes the inertial parameters of the vehicle. And if we don't know those inertial parameters, then we cannot precisely control the vehicle. So that we need to have some state estimation of those parameters online. In addition, wind estimation is important for any outdoor application, such as meteorology. Specifically, one that we've looked at is forestry. Spreading forest fires, predicting the spread of forest fires is basically done using wind velocity estimates. And currently, the methods for doing that are very crude. They involve setting up a tower and a lot of manual labor, and you can only get a velocity estimate at one point in space at a time. But with a quadrotor, you can just send it up and get velocity estimates at varying points. Also, this can be used, wind velocity estimation can be used to plan efficient trajectories that take advantage of the wind direction. So the contributions of this are that we develop an IMU-based unscented Kalman filter that uses the full dynamics of the vehicle, Newton-Euler dynamics and motor dynamics, to estimate things like tilt, velocity, twist, or twist is velocity, and inertial parameters and aerodynamic parameters, and sensor biases. In doing this, we estimate. We have to estimate some forces or some moments acting on the quadrotor that we didn't anticipate would be significant, such as the blade flapping moment, which I'll discuss later, and the moment required to accelerate and decelerate motors. In addition, we'll incorporate VIO into this filter to estimate the wind velocity as well. And then we will present observability. Well, we present in the paper observability analyses that show when these systems are observable, and I'll touch on that a bit in the presentation. So for a literature review, the most important works that we base all of our principles on are aerodynamic modeling, lumped parameter modeling works for propellers. Moses Bangura is a huge work on this, and he did a huge work on this that involves estimating or lumped parameter models for the thrust variation of a propeller as a function of the induced velocity, which is the additional velocity that the propeller imparts to the air passing through it, as well as the velocity of the propeller relative to the air and the angular velocity of the propeller itself. Induced velocity is hard to know, and it's very challenging to capture. And so what we did, our contribution, was to approximate the induced velocity as functions of the other two parameters, the blade angular velocity and the motor hub velocity relative to the air. And we came up with a simpler model for thrust variation using that. In addition, Felipe Martin's work is also important because he models other things like blade flapping moments and things like that as well. For velocity estimation, there are the following works. Abeyordena and Leishman did very similar things where they took these types of aerodynamic models and they've estimated the velocity of the quadrotor projected into the rotor plane. So they only estimated 2 degrees of freedom of the velocity. What Alibert did is he estimated the full 3D velocity using a induced power model for the propeller. And his results are only in simulation, and his model assumes that many parameters are known, which are not very practical to know. So what we do is we don't make the assumption that many parameters are known. We only we we basically assume that all the parameters are unknown, and we do full 3D velocity estimation using a simple linear drag model that also captures the thrust variation that I talked about earlier. For inertia estimation, there are a couple of works. The most important one is Valentin West, who was a student in our lab, and he did IMU-based state estimation using pose measurements as well for the moment of inertia of the quadrotor. Because he was using vision for this, his system was observable in hover. Therefore, he was able to fly at low speeds, and he didn't see some of these moments, aerodynamic moments that we are modeling that are present during high speeds. So our contribution is that we have a system that is not observable in hover, so therefore we are required to fly at higher speeds, so therefore we have to capture these moments as well. Finally, there are many works on wind estimation for quadrotors. Most of them use indoor tests with most of them use linear drag models, and they test indoors on fans and things like that. We want to capture the wind velocity outdoors with a ground truth sensor measurement, an anemometer, and we want to use the full Newton Euler dynamics to estimate the 3D wind velocity, which very few of these works do. Well, I mean, none of these works really do that in the way that we are doing it, specifically in how we model the blade flapping as an independent effect. So the next work that I'll cover is my past work, which will be somewhat brief. And for preliminary information, I want to basically introduce the world frame, which is an inertial reference frame that is fixed to a point in the ground. It does not move, it does not rotate. But then we have the body fixed frame, B, which is fixed to the quadrotor, and it rotates with the quadrotor. Now, a vector V, shown in red here, can be expressed in either the inertial reference frame, the world frame, or any other reference frame for that matter, but it doesn't need to be expressed in a reference frame. When it's not expressed in a reference frame, we just write V. But if it is expressed in a reference frame, then we write, like over here, we write V subscript or superscript B if it's in the body frame, or V superscript W if it's in the world frame. For example, the orientation of the quadrotor, R, is a matrix whose columns are the basis vectors of the body fixed frame expressed in the world frame. Now, we have the standard quadrotor model, and this standard model that is in most literature only models the thrust forces, these vectors here, and in the weight of the quadrotor, which is this vector, as well as some moments. These moments are drag moments. When the propeller spins quickly, there's a drag that's proportional to the tip speed squared of the propeller. And this moment is used to control, it produces a counter moment on the quadrotor frame, which is used to control the yaw of the quadrotor. The rotation dynamics are presented in the body fixed frame here. This red term accounts for the fact that we are differentiating vectors in a rotating frame, and so we have to compensate for the fact that this frame is rotating. And basically, the reason that we do this in the body fixed frame is because the inertia tensor is expressed as a constant matrix in that frame. So the IMU is obviously an important aspect of our research. And what it does is it has a 3-axis accelerometer, which is given by this mass spring model system here. And it also has a 3-axis gyro, which just measures a biased angular velocity, shown down here. Now, the accelerometer is a little bit more complicated, and what it does is it measures specific acceleration of the quadrotor, which is the acceleration caused by every force except for the weight of the quadrotor. The reason that we have this red GE3 term here is to cancel the negative term, which is in the sum of the forces. And that the reason for that is that when an accelerometer is in free fall, the housing and the mass inside accelerate at the same rate, and therefore these springs do not deflect. And so therefore, the sensor does not sense the effects of gravity. Even though it's accelerating down at 9.8 meters per second squared, it measures 0. Now, the drag model basically takes this standard model and it modifies it with a drag term that is proportional to the hub velocity in the rotor plane. Now, what we do is we assume that the angular velocity of the quadrotor, well, what we did in the past is we assumed that that was small, and that therefore these hub velocities are moving at the same speed as the center, or the same velocity. The hub velocities and the velocity of the center of mass are basically identical at that point. So we model this as being proportional to the velocity in the rotor plane. So VRP is the velocity of the center of mass of the quadrotor projected into the rotor plane. And it's proportional by this constant here. And the reason that it's proportional to the velocity at in the rotor plane is because the reason that it's actually in line with the rotor plane, the force, is because the dominant velocity here is the tip speed squared of the vehicle, or of the propeller. And therefore, that lies in the rotor plane, basically. And that's why this drag force is in the rotor plane. But essentially, when we measure this, when we use this drag force in a IMU-based model, our horizontal component of the accelerometer measures the drag force that is being exerted on the quadrotor. Now, what we did in our ICUAS work is we extended this drag model to account for the variation in thrust due to the fact that a quadrotor, when it climbs in ascending flight, it loses thrust, and when it descends, it gains thrust. Now, the reason for that was explained in my proposal, but basically we modify this model with this red term here, and this red term is basically proportional to the velocity projected onto the B3 axis of the center of mass of the quadrotor. And you'll see that this term actually is lumped together with the drag force that I just mentioned, and the reason for that is because they're both linear. And really, it's important to note that this is not truly a drag force, but it's just a modification to the thrust vector. But it behaves like a drag force. So that's why we lump them together. Now, with this aerodynamic model, what we did is we did aerodynamic control, or we compensated for these aerodynamic parameters in a controller. The left plot here shows some forward flight tests, and what I want you to do is focus on the left plot. These are repeated trials of the same experiment. In red, we have the position error on the y-axis and the time on the x-axis, and we can see that the magnitude of the position error is much smaller for the drag compensating controller shown in red than for the standard controller shown in blue over this trajectory. On the right, we have the same type of experiment, but we're compensating for the change in thrust now, and we are doing vertical flight tests on the right, and you can see similar results for that. So we were able to show that we can compensate for these effects, and that they are indeed significant. We also used our model to do state estimation for the velocity and the tilt of a quadrotor. The left hand, and we did this in a way that is, by the way, independent of the yaw of the vehicle. So the left plot here shows the orientation of the quadrotor. The estimates are in blue, and the ground truth is in green. We can see that the yaw is unknown, so the blue is not overlapping with the green. The blue is just the yaw is assumed to be 0, even though it's constantly varying. And what we can see is that the tilt and the velocity are estimated well using only an IMU and this drag model. And essentially, I want to highlight the fact that we are using a strapped-down, inexpensive, and low bandwidth sensor to estimate wind velocity relative to the air, or indoors, essentially velocity relative to the ground of the vehicle. And this is significant because normally you would have to use vision to do this, and that would incur a lot of overhead. But for completeness, we did use vision for yaw estimation. So essentially what we did is we used the filter that I just mentioned, the IMU-based filter, to boost and to speed up the vision-based algorithm, specifically in the outlier rejection section. So this figure shows a diagram of the algorithm, and essentially, I presented this work in the proposal, so I think I'm going to skip over this. But the point of this is that the outlier rejection was indeed significantly, well, it was, we could show that it was faster, but it also indeed was working because this blue curve is much smaller in magnitude than these red and green curves. The green curve corresponds to dead reckoning, and the red curve corresponds to using vision without outlier rejection. So it's clear that the outlier rejection did improve things, and that the vision was working for the yaw estimate. Now, I'm going to discuss the bulk of my presentation, which is on the recent work that I've done since my proposal. So I want to note here that everything that we're about to cover can easily be extended and trivially be extended to multi-rotor vehicles in general, not just quadrotors. We think it's insignificant, or we think that's significant, but we think that it's doing so is easy and it isn't even worth extra research. I mean, we think that that's such a trivial step, which is really good for us. So the aerodynamic moments of the vehicle are initially the only ones that were considered in the standard model are those due to the thrusts of the vehicle, of the propellers, and those due to the drag of the moment of the propellers. But Felipe Martin models additional moments, and I want to talk a little bit about where they come from, but first I want you to see that they're proportional to this eta I, or this epsilon I. And what epsilon I is it's the direction of spinning of the propeller. So it's +1 for counterclockwise and -1 for clockwise. So if you have a multi-rotor, you have n/2 of the rotors are clockwise and n/2 are counterclockwise. And so therefore, if they're all spinning at the same speed roughly, then this term in blue here cancels. It ends up being half of the terms are the same and they're multiplied by +1 and then half are multiplied by -1. And we have only this red term here that is significant. We also assume that the ambient wind is 0 so that these velocities are the velocities relative to the ground of the vehicle, or of the hub, well, yeah, of the vehicle. So the aerodynamic moments, the red term that I just showed on the last slide can be split into this green term here, which is a blade flapping moment, and the blue term here, which is a thrust difference. It's basically a damping. When you roll with an angular velocity, there's a damping term, and I'll talk a little bit about both of those. So the blade flapping moment basically acts to counter when a quadrotor is in forward flight. It basically is pitching forwards to accelerate or to keep a constant velocity if there's drag. And what the blade flapping moment does is it's in the V cross B3 direction, so that's out of the board using the right-hand rule. And it basically functions to resist the forward tilt of the quadrotor. So that's a little bit of intuition about what the blade flapping moment does. Now the other moment that I mentioned was the damping term. And what happens is due to the variation in thrust that I talked about due to the velocity of the hubs, when you're rotating counterclockwise or clockwise or this is clockwise in this case, this hub has a downwards velocity and this hub has a velocity in this direction, and therefore they exert these drag-like forces. And these drag-like forces cause the moment shown in light blue here, which is again a damping term that resists the direction of angular velocity. Now, the blade flapping is a very complicated phenomenon, and I want to give a little bit more intuition behind what causes it. So here what we see is we see a top-down view of a propeller. Now, the incident wind, the horizontal component of the wind, or the rotor plane component of the wind relative to this propeller is shown here, VHI. And this wind defines an aerodynamic hub frame, AI1 and AI2. I just stands for the ith rotor. But AI1 is in line with this relative wind. and AI2 is orthogonal to it, but still in the rotor plane. Now, the azimuth angle of the quadrotor is defined for counterclockwise spinning propellers as it's counterclockwise from AI1, and for clockwise, it's actually the other direction, which I'll talk about in a second. And basically, what you want to take away from this slide is that when the azimuth angle is 90 degrees, the orange propeller sees a higher relative wind velocity because this is its velocity profile, and you have to subtract from that this velocity profile. So it sees a higher dimension, or it sees a higher velocity relative to the air than this blade in blue. So therefore, the orange blade has more lift than the blue blade. And what this causes is it causes a lift imbalance, and that causes the blade to want to flap as it goes around. But it doesn't flap immediately. This system can be modeled as a mass, as a beam, a hinged beam with a spring. And the flapping angle shown here in red is beta. And basically, there's a lot of literature in the helicopter theory literature about how this system responds, and the responses are have very complicated models. But basically, what I want you to take away from this is that the flapping angle here is in red, and it is represented by a Fourier series where the first three terms are the most significant: beta naught, beta 1, and beta 2. For us, beta naught is small because the propellers are so stiff. This is the coning angle of the blade, so it represents a constant flapping that's independent of azimuth. But the other two beta 1 is the flapping angle when the azimuth is 90 degrees, and beta 2 is the flapping angle when the azimuth is 180 degrees. Now, the moment here in the AI1 direction is proportional to beta 1 because it is the moment reacting on the hub at 90 degrees azimuth, and the beta 2 moment is proportional to, or the beta 2 is proportional to the AI2 flapping moment. And we want to see which one of these is more significant. Do we need to have both of these moments in the model, AI1 and AI2, or can we only take one of them? And what this slide basically shows is it shows a counterclockwise propeller here and a clockwise propeller here. And the point is that the maximum flapping, the azimuth angle corresponding to the maximum flap, psi sub c, is the same for both of these, but in the sense that it's the same magnitude, but it's defined differently for clockwise and counterclockwise propellers. This means that we'll generate these forces shown in red here, or these moments rather, and these moments, when you sum them up, since you have, again, an even number of clockwise and anti-clockwise propellers, when you sum them, you'll see that the AI2 components accumulate because they're pointing in the same direction, and the AI1 components cancel because they're pointing in opposite directions. And this is why we have that the blade flapping moment is in the V cross B3 direction. So now that I've explained the intuition behind the blade flapping, I want to ask, is it significant? We tried to do the estimation without it at first, just to keep things simple, and we thought, well, it's not significant, probably, because these are very stiff blades. Why would they flap very far distances? So what we did is we implemented a Kalman filter that estimates the diagonal inertia terms and a bunch of the other things. The main key I want you to take away from is we're estimating a bunch of things that we know, or that we were estimating a bunch of things that were estimated well with this filter, but these diagonal inertia terms were not estimated well. And that's why they're shown in red. And this ends up being because we ignored the blade flapping moment, and we had such high velocities in our trajectory to keep the system observable. But at first we didn't see this, and we were trying to troubleshoot. So when we were troubleshooting, we thought, okay, well, what can be wrong? Well, we must be if we've implemented the filter correctly, we must be missing some kind of effects that are significant on the vehicle. So how does the filter more or less compute the angular or the moment of inertia of the vehicle? Well, what it does is it regresses the angular acceleration, assuming the Coriolis term is small, which it usually is. It regresses the angular acceleration against the moments on the vehicle. So they're proportional to each other by the moment of inertia j. So the IMU provides a source of information about these moments, in it providing the angular velocity. We can differentiate it and multiply it by our ground truth moment of inertia to get the moments acting on the vehicle dictated by the IMU. And the model that we're using, the dynamic model that we're using for the process, is just the sum of the forces. We're looking at the horizontal components now. So it's just the sum of the thrust induced the moments induced by the thrusts of each propeller. So we computed what these were, and we compared them to each other. We differenced them, and we saw the discrepancy between them here shown in the blue. And basically, what you want to take away from this is that they are oscillating. There is a significant discrepancy, first of all. The magnitude here is significant, and it is oscillating. And we were thinking, well, why is this thing oscillating? And then we thought, well, okay, our trajectory is oscillating. So this is a perfect time for me to mention what the trajectory is that we're flying. So this is what we call a simple Lissajous. And basically what it was is it's something that's designed to be keeping the system as far away from hover as possible, because this is where our unobservability lies. And so we thought, at one point it just crossed our mind, why don't we plot the velocity of the vehicle and compare it to this discrepancy in the moments. And so basically what we saw is that the unmodeled moment here is proportional, like the B1 component of the moment is proportional to the B2 component of the velocity. And the B2 component of the moment is proportional to the B1 component of the velocity. This basically means that there's an orthogonal moment that's proportional to velocity. Well, that looks an awful lot like the flapping moment that we just mentioned. And so that is how we concluded that indeed the flapping moment is significant. And we incorporated it into the filter. We estimated the flapping moment coefficient, and we ended up getting much better results for the moment of inertia. They were the right order of magnitude, and at least in the B1 and L components. But we still had a problem with the. Before I go into this slide, we had a problem with the B3 component. It was the right order of magnitude, but it still seemed off an awful lot. And so I want to now mention what could be causing that. So this is a compound Lissajous trajectory. Now, why would we design a trajectory like this? The quadrotor is constantly oscillating, and what the problem is that in the simple Lissajous trajectory, we didn't hit high enough angular accelerations to really estimate the moment of inertia very well. We wanted better estimates of the moment of inertia, and as I mentioned, we have to regress the angular acceleration against the moment. So we need high angular accelerations. If we take a simple Lissajous and speed it up, we get higher angular accelerations, but we hit motor saturation. So what Jimmy's idea was to take this simple Lissajous and add a higher frequency, smaller amplitude Lissajous on top of that, and that's what this is. Now you can see from this figure or this video that the quadrotor is flailing like a lot, and you can imagine that the motor speeds would be constantly accelerating. The motors themselves would be constantly accelerating and decelerating. Now, this acceleration and deceleration effect is not typically modeled in terms of reaction moments, and so we thought, okay, maybe we should look into that. But from the data, I want to point out that these are both the same figure. This is just a zoomed in figure, but what we're doing is we're looking at the z component of the moments as dictated by the IMU and as dictated by the model. And what we can see is we can see that the amplitude of the blue, which is the model, looks a little bit small compared to the green. And we can also see places where it doesn't quite match up right. Like here, the blue is kind of slightly to the right of the green. It's kind of, it doesn't really middle the green data, if that makes sense. And so things like that kind of made us think, well, okay, we can probably do a little bit better. Maybe this, there's something to this. Maybe this angular acceleration is what is missing. So what we did is we modeled this angular acceleration of the propeller. And the takeaway here is that it is proportional to the moment of inertia of the blade and the motor. And it's also proportional to the angular acceleration of the propeller. This moment here is. And it's in the B3 direction. And what we did is we added the moment, the angular velocity derivative, and the moment of inertia to the state of the vehicle. We showed that it was observable. Well, actually, I take that back. Let me walk that back. We had a hard time showing that this was observable because this model requires unknown control inputs. So I'll talk a little bit more about that later. We basically showed that something similar was observable, which I'll talk about in a second. But the point is that we added these to the state, and then now you get the difference that you see on the left and the right. So you can see that the right is much better than the left. So the left is before we added this effect, the moment comparison, and the right is the moment comparison after we added this motor acceleration effect. So you'll see that the thing that I was talking about earlier, this the amplitudes, first of all, being small, is kind of fixed here. And then the fact that this, at this moment, this is just my toy example, but here it's off to the right of the data. Here it's kind of middling it. So this kind of fixed the problem. Essentially what you want to take away is that there's some high frequency components that were not captured in the green data by the blue that now are captured. So I mentioned that we tried to do an observability analysis, but the previous system, which was a little hacky, required unknown control inputs, and that ends up being more computationally difficult to do an observability analysis with. So what we did is we said, okay, we know our commanded motor speeds, and we know we have measurements, RPM feedback on the quadrotor. So what we're going to do is we're going to come up with a better model for the motor dynamics. Basically, what we're doing is we're modeling the motor controller on board, which models the torque being applied to the motor as being proportional to the error in, well, here's the torque being applied to the motor down here. It's proportional to the error in the RPMs. And also, there's a feed-forward term, which is the drag moment term that I was talking about earlier. Now, essentially, these are the motor dynamics. The drag term down here cancels with the opposing drag on the blade here, and all you have left is this torque required to accelerate the motor. And this was easy to show that it was observable. So we were able to show observability of this system, but it is not observable in hover, as I mentioned. So now the full Newton-Euler unscented Kalman filter basically is shown here. It's estimating the tilt. It's estimating the twist of the vehicle, which is the linear and angular velocities. It's estimating the IMU biases, so the accelerometer and the gyro biases. It's estimating the motor speeds. And it's estimating inertial parameters, including the position of the center of thrust relative to the center of mass, and the position of the IMU relative to the center of mass. And it's also estimating the other parameters like the torque coefficient to the motor and the aerodynamic parameters. So altogether, this is a 32-dimensional state. Now, the process model here is the position and the attitude kinematics, the tilt kinematics specifically, and the dynamics for position and the orientation. The dynamics for position are shown here. And what was previously unmodeled, as I mentioned, was the fact that each of these hubs is moving at a different velocity from the center of mass. But now we're capturing that. V sub I is the velocity of the ith hub. So it is just the velocity of the center of mass plus omega cross r. And what you'll notice is that these forces are not in line with the rotor plane. The reason for that is because these forces don't just consist of the thrust of the vehicle or of the propeller. They consist of the drag forces acting on the propeller as well. So that's why I intentionally drew them that way. The process model also includes the attitude dynamics. All of this was new in our model, but specifically what is not modeled in the literature is shown in red here. The flapping moment and this part of the yaw moment, the part required for the angular acceleration of the motors. The other important moments are those caused by the forces acting on the propellers. Those are the other important moments. And the measurement model is shown here. So the IMU is the first measurement. It's the most important one. And what it does is it measures the thrust and the drag. But it also, since on our platform, the IMU was quite off-center from the center of mass, we have to estimate this position of the IMU relative to the center of mass as well. And it is estimated through this correction term, which is the acceleration of the IMU relative to the center of mass. And a lot of you have seen this before. It's just the centripetal acceleration plus the tangential component of acceleration of the IMU. We also have biased motor speed, or biased angular velocity, and we have a motor speed measurement as well. So when we tested the filter, what we did is we took the quadrotor and we just flew it around, and we estimated the moment of inertia and the other parameters. And then what we did is we added masses to the quadrotor, and this changed the mass and the moment of inertia of the vehicle. So we added these metal nuts shown here along the booms of the quadrotor, and we used the parallel axis theorem basically to compute roughly what is the change in moment of inertia that these masses would cause. And then what we did is we flew the quadrotor again, and we predicted what now the new moment of inertia will be up here in red. And we basically said, okay, is the estimated value in blue, does it converge to the value in red, more or less? And so you'll see over time that it is converging. Also here is shown the ground truth versus the filter for the velocity of the vehicle. But you'll see after some time that yes, the more or less, even considering the fact that our measurements had some, or our predictions have to have had some error because we're using an approximation from the parallel axis theorem, yes, these moments of inertia are being estimated properly. So that covers my work on inertia estimation, and now I want to talk about wind estimation. So wind estimation uses a simple concept called the wind triangle. And basically, the wind triangle is basically saying that the velocity relative to the ground minus the velocity of the wind is the relative airspeed. So the velocity relative to the ground is in blue here, and it's given by VIO. The velocity of the wind relative to, or the velocity of the relative airspeed here in red is given by the IMU. Really, the entire time we assumed that the wind was 0, but now the IMU is, if we lift that assumption, the IMU is measuring relative airspeed to the quadrotor. And this velocity is the wind velocity. And we can obtain it from these two just with vector differencing. So the approach that we take is we do a measurement update with VIO. It's just a pose and a velocity measurement. And then what we do is we take all of the parameters that we mentioned earlier and we freeze them. We set them to known values so that the system is observable in hover in this case. And we discard the motor dynamics because we're no longer flying crazy trajectories to estimate wind velocity anymore. We can just hover or just fly casually. And then what we do is we just slightly generalize the models for drag and blade flapping by assuming that they have different coefficients in different directions. And then we basically use the wind triangle. So every time we had a velocity relative to the ground before, we say, okay, that's a velocity relative to the air now. And and then we use the VIO to get our velocity relative to the ground. And we flew outdoors with the anemometer shown here on the right, and we had the quadrotor flying around in circles. We also had hover tests, and essentially we placed the quadrotor near but not too close to the anemometer so that it wouldn't interfere with it, and we wanted to hopefully make the assumption that hopefully since we're in a large open area, the airspeed is kind of continuous. It's kind of the same everywhere, spatially invariant. So here are a lot of plots. Each of these plots corresponds to a data set in hover. And basically, the red is the anemometer reading for the wind velocity, and the blue is the filter reading. So this is how our filter performed in hover on estimating the wind velocity. One thing to note is that it does better in the x and the y directions than the z direction. This can be because of bias caused by unknown thrust, like an error in the thrust coefficient, basically. I think that's what this bias is caused by. And the other thing to note is that z velocity when estimating wind is not as important as x and y velocity is. So also we have the test done from flying in circles. Each of these is a data set. And you'll notice that there is there does appear to be something that looks like a delay to some degree. I think overall the data looks good, but I think that there is a delay. And I think that this delay could be caused by the fact that because we were flying in we had a larger footprint when we were flying, we had to space the anemometer further away from the quadrotor. And that this delay could be caused by the fact that the wind speeds weren't super high, and if the quadrotor is 4 meters away from the anemometer, it might take a few seconds for the wind change to affect things. So in conclusion, we developed an inertia estimation framework that requires no pose measurements. It uses the full Newton Euler dynamics. It basically we tested it on a quadrotor by changing the moment of inertia and the mass of the vehicle. And we extended this to a wind estimation filter by adding vision. For future work, we want to investigate scaling effects. So as we scale down the quadrotor, other aerodynamic effects could become significant, like the parasitic drag, which is the drag caused by non-aerodynamic surfaces. And we want to look into it as well. Instead of using common filters, we want to look into using geometric nonlinear observers. We want to look into basically following an integral curve of a wind field as well. So that's why I call wind surfing. So if you want to just explore if you're a quadrotor and you want to go a long distance, if you follow the wind, basically you have an efficient trajectory. And you can do that for a longer period of time, get further away. So these are the relevant publications. Some of them are still in the works, like these top two, but the other ones have been published. And I want to acknowledge people. Do I do this now or after? Okay. So I want to acknowledge my advisor and my mentor, Vijay Kumar, for his support throughout my PhD career. I want to also acknowledge Giuseppe Loiano, who has been my co-mentor and has taught me a lot. I want to acknowledge my entire committee for being here and for their valuable feedback. I want to acknowledge Jimmy Paulos, who helped me a lot on the inertia estimation project. I want to acknowledge Stephen Vybov and Guy, who helped a lot for wind estimation. And I want to acknowledge my parents and my family for their support as I've done my PhD career. And I want to acknowledge all my friends in GRASP, many who are here, and just everybody, even those of you who I don't know who have attended today. Thank you so much for coming out. With that being said, I would like to end my presentation and take questions.
We're going to start with questions from the audience. So this is a public portion of the hearing.
Justin. Thanks.
I wanted to start, I have a couple questions. I'm going to try to not ask all of them at once. So it seems like you're really able to estimate many of the inertial and aerodynamic parameters online. I'm wondering if you thought about incorporating that into the book and being able to improve performance of the vehicle in that approach as well.
Yeah, we've thought about it. We just haven't. We just didn't get to it. But that's an obvious extension of this work that I should have mentioned. Is in addition to inertial parameters, aerodynamic parameters are critical for following trajectories with low tracking error. So we would like to in the future nest this this estimation framework with a control loop. So challenges might include perhaps like a delay in the state estimate affecting the controller. If the state estimate isn't quickly converging, then the controller, well, at least for like velocity and things like that, the controller could end up suffering from that. And so really, the separation principle applies for linear systems, right? That you can separate an optimal observer from an optimal controller, but it doesn't really apply to nonlinear systems very well. So finding a better way of combining a more adaptive control-based way of combining this state estimation with this control would also be very helpful. Any other questions? David. Good point. I was thinking when I said that, I was thinking specifically of multi-rotor systems where there are coplanar propellers. If the propeller is tilted, I think it would still actually work, but I think it might be a little trickier. I mean, you would have to just model the transformation from the hub frame to the center, to the vehicle's body frame, and you would. Are you talking about fixed tilt or variable pitch? Okay. So for a fixed tilt, I think it would still work. I think the biggest thing that's important is that you have an equal number of even and odd, or of clockwise and counterclockwise spinning propellers. I think that's a really important thing. Yeah.
Any other questions from the audience? Okay, so we're going to go to the public portion of the committee questions. So this is everyone who's officially furthest from us. Who gets this question?
So do you think that it's possible to, let's suppose that the vehicle interacts with someone, do you think it's possible to, insert as well an external forces acting on the platform?
It's possible. Frank Shen did something like this in just modeling general disturbances on the quadrotor, just with a Kalman filter variant. We would like to, his model was kind of like, okay, it's like a random walk. The disturbance is like a random walk, and obviously that wouldn't cut it really if you were dealing with like people in human-robot interaction. So obviously, I think you would have to use some like visual cues to determine like roughly, okay, where is this, maybe the person wants to grab the quadrotor. Okay, well, the force vector is going to be along maybe the length of the arm or something like, something like this. I think you would have to have some kind of model and some way of predicting things better in order to get that to work properly.
Yes. Slide 35.
Yeah.
So this here you're using M, an estimate of M. So this estimation is done incrementally like a filter, or is it like a least squares?
So it's actually just instantaneous. It's just, so when we're plotting these things shown here, we're just at each step of the filter. So any quantity that has a hat over it is an estimated quantity. So what we're doing is we're taking, what we did is we took the known position difference and we crossed it with the thrust that we knew at each time, right? And we said, okay, we summoned that up. That's the moment as dictated by the model. So the thrust was filtered. Yes, it was filtered because the KF at the time we were estimating the KF value of the propeller, and so that was filtered, and we assumed that we had instantaneous like feedback for like the motor speeds.
So the P hat has an integration inside it over time, while the other one is just a difference, right?
Right. The accelerometer
But the
is.
omega has an integration from the filter probably.
The omega has some integration and some smoothing from the filter. And so that we didn't just take the gyro and difference it because that would have been horrible.
Okay,
Yeah.
that's great. 49. So can you, what was before that, what was the state vector here?
The state vector here was it was this vector here. So it was the tilt, it was the twist, so angular and linear velocity. It was the accelerometer and gyro biases. It was the motor speeds. It was the mass, the three components of moment of inertia. We assumed it was diagonal because we had bilateral symmetry. It was the moment of inertia of the propeller and blade, position of center of thrust relative to center of mass, position of IMU relative to center of mass. These are the drag coefficients. This is the blade flapping coefficient, and then this is the torque coefficient for the motor controller.
And the J's ideally would be derived from the previous, from the J omega dot equal M.
Ye-
One, one,
ye-
two, J.
Yes.
So if if there was a package and something would move inside the package, it would be readjusted.
I think so. Yeah. I think if you had that, then the moment of inertia of the vehicle would not be a constant as well. So you need to assume that things are securely stored in the package. But I think it could be readjusted over. I mean, but if it's constantly moving, then I don't know if it's going to converge to that readjustment quickly enough.
What's the rate of convergence of your estimate?
So it took a bit of time for this thing to converge, and I think partially, it's I don't know exactly the number, but it seems like after about 5 seconds, it gets about
That's the question you asked.
right. After about 5 seconds, it seems to get about like 80 to 90% of the way there. So.
So
Yeah.
the UKF itself, does it have a temporal window, sliding window, or is it just updated after every IMU measurement?
After every IMU measurement, it's updated.
So guys, I never understood why but we are using, at FLA we're using a window with an SKF, right?
In the what?
At FLA.
No, that's the vision problem.
That's for the VR, because here, but here you use
Just for
This no, not for this. This for the wind estimation we use vision. Yeah.
And in P3 with the triangle with V and W. So I'm confused about the I in the V and the IMU in the V minus W. So when you estimate the velocity relative to the ground, the acceleration and the omega you're using as a measurement from the IMU is not the same as the one used in V minus W.
You're saying that the
So in the V velocity relative to the ground,
right.
the accelerometer from the IMU
Good point. That's a good point. So they're used in different ways. The IMU is used in the full dynamic model for the V minus W, and it's used just in a kinematic model for the VIO. And I was actually thinking about this, is this actually a contradiction? But it actually, I don't think it is one, because the IMU is measuring the acceleration, the specific acceleration of the quadrotor in the VIO, right? So, and it's also, it's just, so it's a little bit, this is more like a loosely coupled approach, I think, is the takeaway from this, yeah.
I think the terminology is confusing, so you should fix that.
Okay,
Two different models.
right.
All right. This is really great work and very clearly described.
Oh, thank you.
CJ?
So, I forget what the slide number is, but again, in the modeling of this, you point out that one of the contributions is to take advantage of the blade flapping moment. Can you talk a little bit about what the relative magnitude of that term is as a function of
Sure.
speed or where it becomes?
Yeah. So this plot here is, it says the blade flapping moment is about it's about 1 Newton centimeter to 2 Newton centimeters. And normally, we have a small quad, it's about 250 grams. And if you think about a Newton times a centimeter, well, that's a significant force on this quadrotor. And basically, we compared the, I ended up comparing like here's a good, like the yaw moment here, this is the actual magnitude of the yaw moment. So you can see here that it is around a half a Newton centimeter, maybe at peak in the blue. So really a Newton centimeter, was definitely enough to throw our, 1 Newton centimeter was basically enough to throw our estimates off quite a bit. And that's why we were just getting completely inconsistent yaw moment of inertia estimates from not incorporating the flapping moment.
I wasn't entirely clear whether you get a sort of a different experience at each blade, or is that?
What's that? So for each blade?
Yeah.
If we're considering each blade separately?
Yeah.
Yes, we are. Yes. But it actually turns out that for the flapping moment, Jimmy and I showed this, that if you even, it doesn't actually matter, as long as you assume that all propellers are spinning at the same speeds for the flapping moment, it actually doesn't matter if you're yawing, if you're flying forwards, it actually ends up being a lumped term in terms, we still consider it for each blade because that assumption that they're all spinning at the same velocity could be wrong, so could be violated.
One question I had was, again, in the current model, you are currently estimating actual rotor speeds. Comparing them against commanded speed.
Right.
They show up as something that's been estimated. How much better would life be if you had an encoder or a beam brake sensor that was giving you accurate propeller speeds?
It would probably be better. I think it would be better, but I think I think we could potentially remove, well, I for that because of that motor acceleration phenomenon, I'm not sure if it would be much better actually, because if unless we had some way of getting like an instantaneous reading of the acceleration of the motors, which I don't think is something that we would be able to get, then we would probably still need to get better performance by incorporating that model that filters for the angular acceleration of each motor.
Well, could you imagine getting motor acceleration by monitoring current?
Perhaps you could do, yeah, I think you could do that. Or voltage, right? I think, because, yeah, I mean, the torque is proportional to
Well, either should do it depending on how you model the internal resistance of the motors. But
right. Yeah, I would have to look into motor modeling in a little bit more detail.
you could do the current.
Yeah. What's that? Oh, Matt's motors. Yeah, it's something that I would like to look into some more. Is how to. I mean, I did it a long time ago, but.
One other thing, in some of the plots you showed, particularly towards the end for the wind, they track very nicely qualitatively. I was wondering whether there were quantitative.
We do have quantitative metrics in the paper. So what we do is we take the RMS of the signal, and we put that in the denominator, and we take the RMS of the error, and we put that in the numerator. So we have a way of not just saying, okay, this is the RMS error, but we have a way of normalizing it by how large the signal actually is.
Okay.
The RMS of the red signal in the denominator. So, and that gives us like, that's how we did a lot of these metrics for the filter, like for the inertia estimation as well. It turns out that anything like you can do really well if you're like at 20%, and if you're around 80%, that's not great. If you're around 40%, 50%, that's reasonable for wind estimation with unknown, because we don't actually know what the wind velocity is where the quadrotor is. We only know where it is in the vicinity of a quadrotor at a sampled point. So.
All right, so those numbers do exist.
They do. I put them in the dissertation. At the I put them in. I sent there. That's right there. It's right there. That table, yeah. Yeah, it's right there. Yeah, it's you might have an older version of the dissertation. That might be why. Because I sent one recently, like I think on Friday maybe. I think I sent it out. I'm not sure.
Yeah, I mean, just to check my understanding again, you only need some estimate for velocity for ground speed velocity to compare this against. So this would work perfectly fine with GPS as your source for B.
Yeah.
As it would with anything.
It would, yeah.
As a practical matter.
We just didn't have GPS.
Right.
And I think RTK GPS, was it RTK GPS would be ideal.
Regular GPS, the velocity measurements are fine. Positional
Okay. Okay.
You get it from Svacha over. Okay, yeah.
TJ?
Can I just, I think Justin's question was less about the separation principle for not only assistance, but at the end of the day, what does this buy you? So if you take these new inertial parameters for whatever estimates you have, and then you use that for the control, what's the performance gain? I know you haven't done that.
You mean in real time? In real time estimating them?
Real time. Let's say you do it offline. You put those washers in, you run the experiment, you get the new inertia, and how much does it matter really? And going back to the carrying the payloads, you calibrate, you do it for without the payload, but now you have the payload and you want to run an estimation cycle, and does it really matter?
To answer your question, when I tested so in the experiment where I mentioned that I changed the inertia of the vehicle, I had to retune the controller each time I did it, and I only added like 3 washers on each, or 3 nuts on each boom. So because of that, I would think that it would significantly benefit things, because I had to retune the controllers like completely from just a small change like that. So.
You're not making your case. What you should say is that if I estimate the inertia, I can automatically get a new controller, which will give me
Right.
the following performance gains. I think that's what he's looking for.
Okay. Yeah. I mean, that connection should be said. Yes.
Anything else?
No, that's just
Okay.
that was Justin's question. I was trying to be a little more nuanced about it.
So I'm gonna save my questions for the private section. So this concludes the public portion. So thanks again to the audience for showing up. And then so we're gonna ask the audience to leave. If there's anybody online, we'll have to ask them to.
We'll kill the stream right now. Okay, you'll get it, Justin? Okay.